through the entire worksheet in the previous classes. I was only able to get through the first page, but I think the second page is helpful. It's important too, because there's some things that require the calculator in terms of finding the bounds that we're not going to experience on the first page. So hopefully we can get to some of the problems, those problems on Monday. Okay, so let's look at number one. Oh, I do want to point out this. I created a document on the website. I may continue to update this, but I want to start going over this first. I think I went over this yesterday, but just as a reminder, these are the most common pitfalls, common mistakes that I see students make, and I'll kind of go over these this list first. When you're drawing your radius, especially for, this is especially for washer method, just because there's that additional complexity of working with that second radius. You got to subtract out the whole, and there's just more ways to make mistakes when there's more things going on. So when drawing your radius, always include and always connect to the axis of revolution. I think the tendency is sometimes students want to just connect that distance between the two curves because that's what we experience with area. That's what we experience with this method, but not for washer method. Okay. And also, sometimes students are not recognizing the fact that the axis, even though it's sitting, looks like it's sitting at the edge of your diagram, it's really the center of your diagram, because that shaded region is going to end up rotating to the other side that you're not seeing, and that's going to truly make your axis the center. So make sure that we never just connect between the two curves, because that's never going to be the radius. You're always going to have to extend outside the shaded region to be able to reach that axis of revolution, because of the fact that our axis is going to be disconnected from our shaded region. Second is make sure that we are using appropriate washer method formula. I think I see students, we have to make sure that we square each of the radius separately. Sometimes students feel like, well, I mean, it's easier if I just subtract the radius first and then square it, just less keystrokes. But these are not the same things. Okay, the reason why we can't do that is because these are not the same thing. If I were to FOIL this out, I'll get big R squared minus 2 big Rx, little rx plus R squared, and that's not the same thing as R squared, big R squared minus little r squared. So we don't want to do this, right? We want to rely on what the formula tells us to use. Your axis of revolution has no role. It plays no impact on the bounds of integration. Your bounds is purely dependent on the boundaries of your shaded region. So you may, your object may be a lot larger because your axis is all the way out. And whether it's this method or washer method or area, we find bounds the same way. We just look at the shaded region. And sometimes students get thrown off by the axis because they look at the axis and they feel like it's got to play a role in the boundary somehow. And so they try to find a way to work that in. But ignore the axis when you're trying to find the bounds. Doesn't matter where it is. It doesn't matter if it's washer method or this method. And we'll see an example of that on the bottom of this first worksheet, or today's worksheet. Next item, just because our axis of revolution is touching the shaded region does not automatically mean that we're dealing with this method problem. Okay, so a disk method is only when the axis is up against a flat surface of the shaded region. That's the only time we can guarantee that there's no gap. But if your axis is up against a curved region, it is washer method, even though you may feel like, well, it's touching, so it's got to be disk method, right? So that statement is only partially true. If it's touching, but there's a gap, then we have to, that's going to fall in washer method territory. So let me just give you a quick visual example here. In both these graphs here, the axis is touching the shaded region, but we have different methods for these. Here it's touching, but it's up against a curved surface, so there's all this gap that's being left unaccounted for. So we have to subtract that out. We got to go through washer method. Here the axis is up against a flat surface, there's not an inch of space between, once everything gets rotated, there's no space between the axis and the shaded region, so there's no need for a second radius. All we need is one radius, big R, for this. Okay, so I'll make sure that we can see that distinction and understand that we don't want to be using this method when something calls for washer method. Okay, next item. Remember, when you have a horizontal radius, you have to adjust your equation. Your equation that's in the form of y equals is perfect for top minus bottom, but it's not set up for right minus left. We got to take the time to rearrange the equation. We got to solve for x. We got to get x's on the left by itself and everything else on the other side. So that's an additional step that sometimes students forget or don't know about, right? So make sure that if you're doing right minus left, you just got to prepare yourself. All right, I got to do some extra work here. It's not going to be as quick as a top minus bottom setup. And then one more thing that I thought of after I created the document is remember to distribute the negative sign through your radius expression, especially with that bottom and that left portion. So always use parentheses, and we'll do that today. I'm going to keep reminding us, put parentheses around your bottom or your left expression, even if you're not going to distribute, even if there's only one term. I think it provides a nice safeguard, a nice reminder that if there were multiple terms, that you're not going to forget to distribute, or it's less likely for you to forget if you see a set of parentheses there reminding you that the negative is going to have to see every term and distribute through your parentheses. Okay. All right, just wanted to point those things out, and hopefully we can, actively avoid these common mistakes. Okay. All right, so let's look at first page here. So at the top, there's going to be a mixture of this method and washer method, and we're going to be able to tell after we look at the dotted line in relation to the shaded region. But I only put washer method at the top. I will put this method, washer method, area. I'll put all the variations on the formula sheet, attach it to your test. But right now, I only put washer method. We are going to use this method, but just to show you, we can do this method if we simply cover up little r squared. If you cover up little r squared, you're staring at the this method formula. So we'll just adapt when we get to a this method problem. Okay, so let region R be the area enclosed by the function y equals root x minus 1. There's that horizontal line, y equals 1, and the y-axis. Find the volume of the solid generated when the region is. So part A, revolved about the line y equals -3. Okay, so for this problem, the axis is drawn for you, but on the test, it won't be. Okay, so all the other examples, it won't be either. You're going to have to draw the axis yourself. You're going to have to make that decision as to where it's sitting. Okay, but most likely I will have the diagram, the shaded region drawn for you, and then you can go from there. Okay, so our dotted line is right up against, is right at -3 here. That's my axis of revolution. We'll put a rotational indication here. Now, we should be able to tell which category we're dealing with. Is this method or a washer method? Washer method, right? There's an obvious gap. This is easy to tell. There's only two scenarios that this shaded region could ever be this method. So I want to kind of show that to you here. It can only be this method if your axis is up against this flat surface, right? So if it's here, if the dotted line is right here up against the y-axis, then that is suitable for this method. There's no gap. And also, if it's up against here, right? If it's up against this y equals 1, then that would also be this method. But If you draw your axis anywhere else, it's going to be washer method. So it's a lot more restrictive to get a disk method scenario than it is a washer method scenario. So even if it's touching, if it's like over here, right at that point, that's still washer method. If it's over here, that's still washer method, right? So touching is not good enough. It's got to be up against a flat surface if you want it to be a disk method problem. Okay, so washer method. That means we have to draw two radius and understand that when we draw a radius, we have to involve the center of your diagram, your axis of revolution. So it looks like the edge of a diagram, but it's really the center because this shaded region is going to end up rotating and going to end up on the other side as well. Just to give a visual, you don't have to draw it, but right, there's this portion that we're not seeing. Right. After everything's said and done, there's going to be kind of a circular ring with a complete gap in between. But if you look, right, this is the true center of your ring. All right. So we're going to have to involve the center as we draw our radius. So extend from the center, your axis of revolution, to the further boundary of your shaded region. And we'll call that big R. Okay, next up, we need little r. Now, let me put this down here, big R of x. Okay, we also need little radius, and little radius, we're going to extend from the axis of revolution, right, starting point here, but we're going to extend to the closer of the two boundary, and we'll call that little r. All right, any questions so far? We see vertical radius in front of us. We know we can just work with the top minus bottom format. This is the easier format. No need to readjust our equations. Our equations are nicely set up for us to use. So let's start building our big radius. Okay, so we look at the top of big radius. What is that touching? Y equals 1. So that's going to come first. So top minus bottom, top minus parentheses. That's a good habit for us to have. And what's the bottom of big radius hitting? -3, right? So even though we're not distributing through multiple terms, I think having that parentheses is helpful, right? Kind of helps us see, oh, I got to deal with two negatives here. I got to resolve those negatives. It's going to become positive. So -1 plus 3 will give me 4. So yeah, so I think even in situations where there's only one term, sometimes it can be helpful in helping us see resolution that has to occur. Okay, little radius. Okay. What's the top of small radius sitting on? Mm-hmm. Oh, and then make sure, I almost made a mistake here. Make sure that your -1 is sitting cleanly outside the square root, right? So that's going to be a distinction to be aware of when you're plugging the calculator as well, that your -1 is safely outside the square root. Okay, top function, root x minus 1, minus big parentheses, bottom function. What's the bottom of little radius sitting on? Yeah, y equals -3, yeah. So again, I mean, parentheses is helpful here. We can distinctly tell that there are two negatives we got to resolve there. So root x minus 1 plus 3 is root x plus 2. All right, we have big R, we have little r, we have everything set up, but we still need what? Bounds, okay? We're going to add up infinite numbers of these circular rings from one end all the way to the other end. What's the furthest left that we see?
0.
0. And what's the furthest right that we see?
We don't have that. I guess 4.
It's 4, yeah. So in this case, it's drawn for us, but let's just get that practice in. What if the number what wasn't here? Yeah, we'll set them equal. So let's just practice setting our equations equal and finding the bounds by hand. You can also use your calculator to find the intersection. You can also use NumSolve on 36 Pro. So find intersection. Okay, so I'll say root x minus 1 is equal to 1. Okay. Add 1 to both sides. I get root x is equal to 2. All right, square both sides. I get x is equal to 4, and that matches with what we see in front of us, right? So we go from left bound of 0 to the right bound of 4. So those are x values, and those are the boundaries that we need to match what we need for top minus bottom washer method. Okay, so here's our volume formula. Pi, definite integral from 0 to 4. Okay. Again, the formula says to square the radius separately, so we need to do that with a minus in between. Big radius is 4, little radius is root x plus 2 dx. Okay. Whichever calculator you're using, just make sure you're spending the time to actually practice entering these in. With the 84, I like to have y1 and y2 hold my big radius and little radius, and then just use the template that I have that I've entered in once, and I was just going to keep calling that same setup for washer method on the home screen. Okay, so I'm going to let y1 hold my big radius. I'll let y2 hold my little radius. Go back to my home screen. I already have my washer method set up. I'm just have to adjust the bounds. So I'm just scrolling back, calling it, scrolling back, going from 0 to 4. Let's see, will it convert to a fraction? Okay, it doesn't, so we'll leave it in decimal form. Okay, don't forget about the pi, and then units cubed. All right, anybody have any trouble with their graphing calculator or their scientific, their 36 Pro? Yeah, I just want to point something out here. Anytime you're dealing with washer method, you're always looking for 3 equations to insert into your radius formula. So we're always going to have 3 equations. So look at the ones that we used here. We used y equals root x minus 1. We used y equals 1, and we used y equals -3. Right, and the reason for washer method always involving 3 separate equations is because we're always involving the axis of revolution, right? So that's shared, but then it's going to extend. One radius is going to extend to a further boundary, another is going to extend to a closer boundary. So those will be different, but then you have a one shared one. So that's why you're always dealing with 3 separate equations. Okay. Okay. So just want to point that out. All right, part B, same shaded region, but now we have a different axis of revolution. So AOR is at x equals -1. So that's going to be a vertical line. So that's going to change the way that we approach our problem, right? The way we draw our radius, the equation that we use is all going to be kind of flipped. Okay, so let's draw our axis. Vertical line right at -1. Okay, we're going to decide washer method or this method. Still washer, right? The only chance that this could be this method is if it's up against this flat surface or up against this flat surface. Anywhere else, it's going to be washer. Okay, good. Washer method. Oh, just want to point out, if you're working off the key, working ahead, my key is incorrect on this problem. I'll make that change and upload it, but I made a mistake for the answer. So if you're looking at the key, trying to match your answer, that's why. Okay, so we have to draw our radius. Our radius is always going to be perpendicular to our axis of revolution. So in this case, it's going to have to be horizontal. So we'll start on the axis. This is the true center, right? This shaded region is going to end up flipping over to this other side. So we're looking at the center here. Extend from your axis to the further boundary of your shaded region. And we'll call that big R of Y, since we're dealing with the horizontal radius here. Adjustments need to be made. Little radius, again, start at the center, start at your axis, and you extend to the closer of the two boundaries. And we'll call that little r. All right, we have the equations for these lines and for these curves, but are they properly set up for what we need?
No.
Not yet. Okay. We need them to be in this form. We need them to be x equals. So we need to make some adjustments. The equations in front of us, we're using them, but it's not in the proper form. So we have y equals square root of x minus 1. That's the radical, that's the curve. But how would you begin to work towards solving for x? Yeah, let's add 1 to both sides. Followed by, what you do next? Yeah, square both sides. All right, careful. We can't just distribute the 2 through and call this y squared plus 1 squared. Okay, you could flow this out, but I don't think it's worth the trouble, right? Just leave it in this form. You'll just deal with that extra set of parentheses. I think it's cleaner this way. So we'll say x is equal to parentheses y plus 1 quantity squared. Okay, I'll point to what that's referring to. Okay, so we have equations in the proper form. If we're missing anything, we'll catch it when we build our radius, but let's build our radius and see if we need anything else. Okay, so right minus left. What's the right endpoint of my big radius sitting on?
Y plus 1 squared.
Okay, y plus 1 squared. Minus parentheses, always protect your bottom or your left equation in a set of parentheses. Okay. What's the left endpoint of my big radius sitting on? -1. So looks like this parentheses is going to be helpful, right? Helps us see more clearly. We got to resolve those two negatives. So plus 1. Okay, so there's my cleaned up version. I'm not going to spend the time to FOIL this out. This is good enough. Okay, it does mean that you got to do another set of parentheses in your expression, but I think it's worth the trouble. So we'll leave it in that form, little r. Okay. What's the right endpoint of little radius sitting on?
0.
X equals 0. Okay, let me point that out. Zero minus parentheses, left endpoint of little radius, -1. Again, we got to resolve those two negatives. The parentheses helps us see that a little better. So 0 minus a -1 is just 1. Okay, so look at this pattern here. Every equation that we used has the proper form of x equals, right? X equals, x equals, x equals, and 3 equations, right? We're always going to be involving exactly 3 equations when we build our 2 radius for washer method. Okay, any questions here? All right, let's build our volume equation. V equals pi, definite integral. Now the bounds, right? We need the bounds. Well, we found bounds from part A. Can I use 0 to 4? Good, right? If we're doing washer method for right minus left, look at the formula. The formula calls for y. 0 and 4 in terms of x, right? That's perfect for top minus bottom, but it's not perfect for right minus left. So we need to think of it as we're adding infinite numbers of these circular rings from the bottom all the way to the top. All right, so what's the lowest y value that you see? Yeah, -1. We can tell by looking at the graph. We don't have to set anything equal. And what's the highest y value that we see? 1. So -1 to 1. Okay, let's build the rest of our formula here. Big radius squared minus little radius squared. So I need to see this notation. I need to see this written out. Even though you're entering into the calculator after this point, I do need to see your expression written out correctly in the correct variable. Okay. All right, any questions? Okay, let's move to our calculator and practice entering this in. So yeah, this is just something you got to be aware of. On the 36 Pro, you may just need to deal with some additional parentheses. It's going to look a little messier, so you got to be careful with your parentheses. Okay. But this is something that more easily avoidable on the graphing calculator because we're able to separate into different places here. So I'll let y1 hold my big radius in terms of x, of course. And little radius 1. Go back to my home screen. Use the function that I used or use the expression that I used already. Just need to adjust the bounds. Let's see, does it convert to a fraction? It does. So there's my volume. Okay, any questions? All right, let's go to the bottom of the page, number 2. So I have the 2 graphs shown, the parabola that's opening down with a vertex at 0, 3, and the y equals -2. But I'm going to just go ahead and shade this in to make it easier for us to see what boundaries we're dealing with, because the X and Y axis, the origin is not part of our boundary here. Okay, we're going to revolve this shaded region around the line y equals 3. And it looks like it's just going to skim the surface of the vertex of my parabola. Okay, first decision we have to make, this method or what? Still all this gap, right? And this is one of the things that we gotta be aware of. If it's up against a curved surface, that's not good enough for this method. It's gonna be washer method. Okay, all right, so. All right, okay, so we know it's washer method. We're gonna have to draw 2 radius perpendicular to our axis. So start on the axis and move to the outer boundaries. Move to the 2 boundaries. Now remember, again, this is the center of your diagram. Technically, after everything is said and done, there's going to be this portion that's also showing, right? There's going to be this object, this kind of the circular ring, but then without a gap in between. It's touching, but there's still a gap that we got to still consider. So we know it's going to be washer method. Let's go ahead and draw our big radius. So start at the center of your object, which is the axis, and we're going to extend to the furthest region, furthest boundary of your shaded region. Okay, and I'll call that big R of X. All right, we need to draw a second radius because we're dealing with washer method. So again, start at the same point, start on the axis. Now we're going to move to the closer of the 2 boundaries, so here. All right. Top minus bottom, vertical radius. We can rely purely on the first method, so it should be easier because the equation's already set up for us. There's no need to rewrite our equations to get it ready. So let's
wait, Mr. Yang, where is the boundary for little r of x?
It's hitting the parabola. Right.
Okay. Okay.
Right. And we can't do this, right? We cannot go from one end of the boundary to the other, right? If we do this, then it's something else, right? This is not the radius. You've got to involve the center some way or somehow whenever you draw your radius. Yeah, I know that this is tempting, right? You want to just connect these two because we see it so often in area and this method, but it's not going to apply for washer method. Okay, one end of your radius has to include your axis. Okay, big R. What's the top of big radius sitting on?
Or well, the top would be
Y equals 3. Okay. Yeah. So top is 3 minus parentheses. Always a good habit there. And the bottom, like you said, is a -2, right? The bottom of the big radius is sitting at that bottom line there, which we know is y equals -2. Okay, I think the parentheses is helpful. seeing the two negatives separated, we can realize, oh, I got to resolve those two negatives there. 3 plus 2, I get 5. Little radius. Okay. What's the top of the radius sitting on? 3, okay. 3 minus big parentheses. Right. What's the bottom of the radius sitting on?
3 minus x squared.
Yeah, sitting on that curve, right? Sitting on that parabola. So I'm gonna just point to it and name it. Three minus x squared. So here you see how there's multiple terms for my bottom function. So this is where parentheses is really going to come in useful, right? We're going to have that extra reminder. I got to distribute that negative through the parentheses. So 3 minus 3 plus x squared. So my radius is x squared. Okay, we have big R, we have little r, but we still need what? Bounce. Okay. How can we find the bounce? Yeah. Set the curve equal to the line. We're looking for these 2 points, and those 2 points is simply the intersection of the horizontal line and the parabola. Okay, find intersection. Three minus x squared is equal to -2. Subtract 3 from both sides. Divide both sides by -1. I get x squared equals 5. What next? Square root. And what happens with square root? Plus or minus. So we're looking for 2 intersections, and perfect, right? We have 2 intersections showing up for us to use. Okay, I think we're ready, right? We have everything that we need. So volume, pi, definite integral, left bound to right bound, smaller to larger value, big radius squared minus little radius squared dx. Big radius is 5, little radius is x squared. Again, square your radius separately. Don't try to take the shortcut and subtract the radius first and then squaring. Right? I think I have this saved up here somewhere. All right, so -√5 to √5. I just had to adjust for my bounds. Oops, I didn't change my expressions here. So my big radius is 5. My little radius is x squared. Does it convert to a fraction? Doesn't. Okay. Okay, questions? Right, Washer method. So we knew we had to deal with 3 equations, all in the form of y equals, and those are the 3 that we used. Okay, questions so far? Guys, I want to point something out here. This is something that a student brought up in second period, and the question that the student raised was, do I need to do something different if the axis is above versus below Don't I have to flip things around and change the order? And the answer to that is it's actually not that important what you do first. You can do bottom minus top, you can do top minus bottom, because we're always going to be squaring it. For washer method and for this method, the order that you subtract is not that important. But the reason that I'm doing top minus bottom is because we've been establishing that phrase ever since area, and we definitely need it for area. We got to do top minus bottom, right minus left. And I just transferred it into volume as well, because it's just easy structurally to just always refer it that way. But ultimately, if you did bottom minus top, if you did in a different order, and you subtracted those in a different order, you're going to get the same thing that I did. Okay, so but just for simplicity's sake and for to keep it more structured, I'm just always just doing top minus bottom. Okay, so that's why. But however, having said that, we still need to make sure that if you want to do bottom minus top, that whatever comes after for your radius expression, you still need to have that in a set of parentheses. Okay, so that we can't get rid of. So if you want to do bottom minus top, then you want to put your top function in a set of parentheses so you distribute the negative through. Okay, but for simplicity's sake, I'm just using top minus bottom for all my radius. Top minus bottom or right minus left to determine all my radius. Okay, one last one here. Revolve about the line y equals -2. Now y equals -2 is all the way down here. It's my AOR. All right, we got to make a decision here. This method or washer method?
This method.
This is this method. Good. So I purposely have these examples next to each other because I want you guys to see that subtle but important difference. They're both touching, but only one is up against the flat surface. Only one is going to allow for no gaps, no holes, no need for subtracting anything out. Here, we got to subtract something out, even though it's touching. All the space we gotta keep in mind to deal with that space by subtracting the hole out. Okay, so this method. So all we need is one radius. We look at our axis is horizontal. We know our radius is going to be perpendicular. So we're just going to make it vertical. So start on the axis, extend to the boundary of our shaded region. There's only one boundary on the other side. And that's our big R. Okay. All right, what's the top of big radius sitting on? 3 minus x squared. Minus parentheses. What's the bottom of big radius sitting on? -2. Right. So yeah, so we're seeing that the parentheses is helping every time, right? Just giving us additional reminders that we got to deal with additional negative, or we got to distribute that. So really want to just encourage you guys to keep using parentheses, even though for some problems they may not be used, but it's going to be a nice safeguard. So x squared plus 2. 2 negatives become positive. 3 plus 2 is 5. There's my big radius. Okay, no need to look for little radius, right? We're just going to rely on what this method, which is just, if we cover up little r squared, then we have everything that we need for this method. Okay, what else do we need? Bounds. It's the same. Okay, let me just write this here. So the same intersection, right? -2 is equal to 3 minus x squared. We get x equals plus or minus √5. Now, let me point something out here. Look at the axis of revolution, right? It's in a different location. It's a different problem. It's a different method, but it's the same bounds. As long as your shaded region is the same and your orientation is the same, we're just looking at the shaded region. So this is another good thing to notice. Your axis plays no role at all when you find your bounds. You're just looking at your shaded region. Okay. Good. All right. So volume, pi integral, -√5 to √5. All we need is big radius squared, since we're doing this method. And we'll just insert radius into our formula there. Careful with your parentheses, enter everything in correctly. (59.628 pi) Okay, any questions here? Now, I prefer my preferred form is that you leave pi in your answer, so don't multiply through. But I do want to indicate to you that it's also possible on the AP exam where your answer choice is showing just a decimal value because they multiply the pi through the answer. So just want to point out to you that it's possible that you may see an answer of 187.328, and that would be the correct answer because these are equivalent. So just be aware, that pi is there. I think that's the preferred form that you see on AP exams, but sometimes they may just decide to multiply that pi through, and I want you guys to understand that these are the same things, right? I'm just multiplying that 3.14 into that decimal and getting just one decimal answer. Units cubed. Okay, any questions? All right, hopefully you guys feel more comfortable with this method and washer method. We've done top minus bottom, we've done right minus left. I try to make it where everything is very structured so that as long as you follow each of the steps and you're doing everything you're supposed to, it should be very predictable, right? No surprises. But there are some problems on the back page that require a little bit more work from the calculator part to figure out the intersection where we're not going to be able to find the intersection by hand as easily. We're going to require the calculator, so maybe we can do some of that on Monday. But Monday we need to do cross-section volume, which is a different perspective, but I'm going to try to bring in a lot of things that we did with this method and washer method to draw that connection. And a lot of things that we're doing is going to be same steps, just a different perspective, because we're not rotating anymore, but we're still going to be relying on like the top minus bottom or right minus left notation. Okay, so we'll do that new topic on Monday, but it shouldn't be long. We should be able to start our test review on Monday. We'll have Tuesday to review, Wednesday to review, Thursday's your test, and I'll have review sessions maybe starting Monday. So Monday afternoon, start holding some sessions afternoon and mornings. All right, thanks everyone. Hope you guys have a great day. See you, or have a great weekend. See you guys on Monday.